our last class, we have done with how to transform it. How to transform, we have by definition. So we have by table of transformation, and we have the properties of transformation. What are the properties that we have learned previously? We have learned how many properties? Remember? One? What are those? Okay, first shifting. Other than that, t to the power of n, linear. Okay, so we have learned three properties: linearity, first shifting, and multiplication by t to the power of n. Okay, where linearity we have what? Addition, subtraction, and then we have scalar multiplication. Okay, and then we have first shifting, where it is the combination of exponent atn, ft, and then multiplication by tn. Okay, so we have learned three properties, right? So now, as for today, we are going to proceed how to transform a special types of function. So we have three types of function that we are going to focus on. The first one here is unit step function, and then we have Dirac delta function, and we have derivative function. Okay, so now let's start with this unit step function. So first, what is unit step function? Now we want to proceed on how to transform a Heaviside function, or we call it as a unit step function. Remember, previously we have transformed a piecewise function, right? Where you need to transform one by one according to the definition. Okay, here we have ft equals to 2, 0, exponent for t, right? Refer to the range. Okay, so 2 for t from 0 to 5, 0 for t from 5 to 10, then exponent for t for t greater than 10. So for this type of function, which is piecewise function here, when you apply the definition of transformation, you need to integrate one by one. So now we have this unit step function. So this that piecewise function, okay, that piecewise function that we have learned previously is called, we can call it as a step function. Okay, piecewise function is a step function. Now, unit step function. So what is unit step function? So before we find the Laplace of unit step function, let us discuss the definition. So unit step function is defined by ht minus a is equals to 0 for t from 0 to a and equals to 1 for t greater than a. Okay, so graphically, from 0 to a, it is 0, and from a onwards, it is equals to 1. Okay, so this is the definition of unit step function. So previously, we have piecewise function. Now, in order for us to transform that piecewise function easily, instead of integrate one by one, what you can do is to convert that piecewise function, that step function, into unit step function. So before this, we have piecewise function. Then that piecewise function can be called also as a step function. Now we can express that step function into unit step function in order for us to ease the process of transformation. So what is unit step function again? This ht minus a, where it equals to 0, 1 from 0 from 0 to a and 1 from t greater than a. Okay, clear or not? Any question? Understand, guys? Okay. So now we want to transform a unit step function. Okay. But we can also transform that step function, that piecewise function, to unit step function. So now let's learn how to convert to unit step function first before we proceed with transformation. Okay. So here we consider the step function. Consider this is your step function, right? Now, in order to convert this step function to unit step function, you have to make sure that this equals to 0 and 1, right? Where you just can factorize the function. So first you put G1 outside. Then this one becomes 0, G1 plus 0. We will have G1 again, right? And then this one is G2, so G1 plus what becomes G2? So G1 plus G2 minus G1. So we will have G2 again. Okay, and then this one G2 minus G1. So here is G1, then factorize. Put this G2 minus G1 outside and then put 1 here. So this is a unit step function. We want to have 0 and 1 there. Okay, now it will have G1 plus G2 minus G1, HT minus A. So that one is for 2 function. If you have up to 3 or 4 function, you will have GT equals to G1 plus G2 minus G1, HT minus A1 plus G3 minus G2. Okay. HT minus A2 plus until Gn minus 1, HT minus En. So let's try this example. Now we have Ft equals to T minus 4 from 0 to 2, T from 2 to 4, and 0 T greater than 4. So now we want to express this step function. This is step function to unit step function. So we have this formula. So we have now your Ft is equals to G1 T minus 4 plus G2 is T minus T minus 4, HT minus A1, this is your A1, HT minus 2, okay, plus 0 minus T, G3 minus G2, HT minus 4. So simplify. So your unit step function will be given by T minus 4, T minus T minus 4 plus with 4HT minus 2 minus T HT minus 4. So this is how you express from step function to unit step function. Is that clear now? Okay. Anyone ask question? Right. So now that one is how to express from a step function to unit step function. Now, let's say we want to express from unit step function to step function. Okay. Okay, you know that, right? So now this is a unit step function. Okay, you simplify this in terms of unit step function. How did you know that this is unit step function? Because there is h there. So ht minus a is represented by unit step function. So you know that this unit step function is obtained by g1 plus g2 minus g1 ht minus a1 plus g3 minus g2 ht minus a2. Okay, so you know your G1 equals to T plus 1. Right? And then G2 minus G1 equals to 1 minus T. You know that G1 is T plus 1. So G2 equals to 1 minus T plus T minus T plus 1. So you will have 2. Right? And then G3 minus G2 equals to T squared. And you know that G2 is 2. So G3 is T squared plus 2. So just substitute two step function where you will have G1, T plus 1, G2, 2, G3, T squared plus 2. Okay, and then this one start with A1 is 2. So 0 to 2 and A2 is 4. So 2 to 4. So this is how you convert from unit to non-unit. So from unit step function to step function. Is that clear? So there are difference here between from step function to unit step function and also from unit step function to step function. Okay, are we good? Okay, take your time. So, anyone has question? You got question? Why we are doing this? Because we want to avoid transforming a piecewise function like we did in our previous example by integrating one by one. Okay, so we transform to unit step function because after this, we are going to learn how to transform a unit step function by using property. The range is obtained from here. You know that this is 2, this is 4. So we have A1 here, we have A2 here, right? So you know that this piecewise function always start from 0 to A1, and then A1 to A2, A3 to A4, until T greater than An minus 1. So this is obtained, the range is obtained from the limit in the unit step function given here. Okay? So we start from 0 to A1. A1 is 2. And then 2 to A2. A2 is 4. And then the last one, T greater or equals to 4 because that one is approaching to infinity. Right? Can we proceed? Okay. So now you know what is unit step function. Then we can learn how to transform a unit step function. So transforming a unit step function of ht minus a will give you exponent to the power of minus as over s. All right? Okay, so now let's prove this. So you know that your function is ht minus a. Okay, you want to transform ht minus a. By definition, ht minus a is given by what? ht minus a is given by 0 and 1 from 0 to a and t greater than a, right? So transforming this will give you, by definition, integrating from 0 to a exponent minus st times 0 dt plus from a to infinity exponent minus a st times with 1 with respect to t. So here you know that this one becomes 0. Where does this come from? Transformation based on the definition. right? So just integrate this one. So you will have what? Minus 1 over s, 1 over exponent st, integrate from a to infinity. So you will have minus 1 over s, minus 1 over exponent, minus, then you will have exponent negative as over s. So this is how you transform unit step function. So basically, based on the definition of unit step function, you know that it is exponent minus as over s. So this is only applicable for unit step function. Then, if you have a piecewise function like we have previously, what you have to do is first to convert to unit step function, then you can use this property of transforming unit step function, instead integrating it one by one. Is that clear? For piecewise function, okay, remember we have transformed this piecewise function previously, right? One by one, you integrate according to the limit. But now you have learned unit step function. So what you can do is convert this piecewise function to unit step function. Remember how to convert? How to convert piecewise function to unit step function like this in example 8. And once it is in terms of unit step function, then you can use this property um, to transform. Okay, so let's say this one. Let's say this is a piecewise function, right? This is your piecewise function. Now you convert to unit step function. So if you want to Laplace transform this function, this unit step function, so you just have to transforming t minus transforming 4 plus 4 transforming ht minus 2. Okay. And then this one minus transforming t h t minus 4. So no need to transform by integrating one by one. So you can apply the property of transforming unit step function here, where ht minus a is exponent minus es over s. Directly based on the table here, you have t equals to 1 over s squared. 4 equals to 4 over s. ht minus 2 becomes exponent minus 2s over s times with 4. This one, we are going to use second shifting property after this. Okay, here. You need to integrate one by one, just like we did in our previous example here. All right? Yeah? Yes. We're going to use the value into the equation. Okay, don't worry. We're going to do some example after this. Okay, so now what you have to know right now is how to convert from unit to step function, or from step function to unit step function, by using the definition of this unit step function. Okay, and then you know how to transform a unit step function. All right, so this is the proving process on why transforming ht minus a becomes exponent minus as over s. Okay, so let's take a look at this example. Example 2010, sorry. So you know that transforming ht minus a will give you exponent minus es over s. So now we have ft, ht minus 2 minus ht minus 4. So you just transforming this ft by transforming ht minus 2 minus transforming ht minus 4. According to this property, you know that your A is here. Then this one becomes exponent negative 2s over s minus exponent negative 4s over s. Then this is your x domain function. That's it. Okay. Instead of, okay, if you don't transform this in terms of unit step function, you know that this can be written as okay, without transforming this to unit step function form, you have to integrate one by one of this by using the definition of transformation. But now you know that this is a unit step function, then you just can use this property. Is that clear? Clear not? Okay, so this is transforming a unit step function. Right, so now let's proceed with which one? This one. This one is okay. Now let's do this properties. Okay, if it is a unit step function alone, then the transformation is exponent minus as over s here, right? This one. Now, when this unit step function is a combination of another function f, okay, then the transformation becomes exponent negative as fs here. Okay, so let's prove this. Now, okay, you know that h t minus a unit step function is given by 0, 1 from 0 to a and a and t greater than or equals to a for 1. Okay, now you have ft minus a, ht minus a. So just multiply with ft minus a, 0, 1. Right, so if ht minus a is this, then ft minus a, ht minus a is this. So transforming this will give you, by definition, we want to prove this. So by definition, it is integrate from 0 to a, because this one, of ft minus a, of exponent negative st, ft minus a times with 0 dt plus integrate from a to infinity exponent negative st ft minus a times with 1. Okay, so this is the definition of Laplace transform. We integrate from 0 to infinity exponent negative st times ft. So by using this unit step function, you know that it is 0 from 0 to a, and it is 1 from t from a to infinity. So we just can write this like this. So this one becomes 0, right? Okay, clear? So now by integrating the second part, okay, let's say here, let u equals to t minus a. Then t equals to u plus a, right? And du equals to dt. Okay, so now this will become, this one is t equals to a. This one is exponent. T equals to exponent, right? But now we want to change to u because we want to have in terms of u plus a. So u equals to t minus a. So u equals to t is a minus a. U equals to 0. Here u equals to t minus a. T is infinity minus a, which equals to infinity. So still we have from 0 to infinity exponent negative s u plus a, okay, fu du, all right? Then here become 0 to infinity exponent negative su times exponent negative as times fu du. So this is a constant, then just put exponent negative as 0 to infinity exponent negative su times with fu du. So this is just the definition of Laplace transform, right? Even though we used u here, so that's why it is exponent negative as times with fs. Remember, fs is integrate from 0 to infinity negative st ft dt. But now we have u du, so it is just another fs. So this is how this exponent negative as fs is obtained from transforming ft minus a ht minus a. Is that clear? Okay, take a look first. ft minus a is just a function. Okay, unit step function is ht minus a. Now ft minus a is just another function which is a combination of this, just like in this example. Here we have t, right? We have t ht minus 4. So we have another function of t there. So this one can be ft minus a. Okay, clear. So we use the property to transform this kind of function. If there is another function of unit step function combined with another function, just like this example, it is t. Okay, understand? So actually, this is how we prove. Usually, this proving process is not used as a practice. That one is for your additional knowledge on how we obtain this formula, why we use this exponent minus ASFS. But sometimes, even though it is rare, maybe it can be asked. Okay, but just to let you know. All right. So now let's try this example. The first example here. You know that this is a piecewise function. Now you have convert to unit step function. Now, how can we transform? Okay, let's proceed with this example that we have discussed before we proceed with another example. Okay, you know that this is a piecewise function. Okay, now you have convert to unit step function. Okay, so now from here you want to transform. So by Laplace transform of this function means that you need to transform one by one by linearity, by still linearity scalar multiplication. This one by unit step function. Now this one is second shifting property. Okay, you know that transforming ht minus a will give you minus exponent minus es over s, and transforming ht minus a, transforming ft minus a, ht minus a will give you exponent minus es fs. So now you have a piecewise function, you convert to unit step function, and this is your unit step function. Now you want to transform this, so you need to transform one by one. So based on the table, transforming t will give you 1 over s squared. Transforming 4 will give you 4 over s. Transforming ht minus 2 will give you, this one is 4, so 4 exponent minus es over s. And now transforming t ht minus 4 is mapped to this ft minus a ht minus a. Okay, let's try to do this. So you want to transform t ht minus 4. And this is mapped to ft minus a ht minus a. But as you can see, this is t minus 4, but this is only t. What you have to make sure before you use this property is, if this is t minus a, this one also t minus a. So we need to do some adjustment. So we need to create this t with, okay, you know that a here is what? What is the value of a for this function? A equals to, what is your a? Okay, a is equals to 4. So you need to create this t to become t minus a. So you just can create t minus 4, but without changing the origin function. So you should just plus with 4. So t minus 4 plus 4, still we have t, right? Okay, and then this one is ht minus a. And you know that from here, ft minus a equals to t minus 4 plus 4. Okay, ht minus a is ht minus 4. So now you have the same term of t minus 4 and t minus 4. Okay, so when ft minus a is t minus 4 plus 4, then your ft should be t plus 4, right? Am I right? Then from here, you can have your fs by transforming t plus 4 here will give you 1 over s squared plus 4s, 4 over s. So when this is mapped to ft minus a, ht minus a, the transformation becomes exponent negative as fs. So this one will become exponent negative a s, where a is 4s times with fs. So this is how you transform of t ht minus 4 there. Clear now? Any question? So overall transformation for here will become plus with another thing here. Okay, clear? Anyone has question? Clear, guys? Anyone has question?
Hello, Dr. Sharafina. May you explain again for the part, right bottom corner, the Laplace THT minus 4 map to blah 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 thing.
This one?
Right bottom corner. Yes, the map to yes, this one.
You don't understand?
Yes.
Okay, let's try again. Okay, now what we did just now is transforming this ft. So we transform one by one here, right? Okay, so we want to transform this. Okay, once again, we want to transform t ht minus 4. As you can see, before this, we just transform unit step function alone, ht minus a. But here we have another function together with that ht minus a, which is t. Okay, so we can use this second shifting property. Okay, so now this can be mapped to second shifting property, which is ft minus a, ht minus a, right? Where this is by second shifting property, ft minus a, ht minus a, the transformation become exponent negative as fs. But before you can use this, you have to make sure both function f and h there must have equal term of t minus a. But in the In the function here, we have t minus 4 and only t. Okay, for ft minus a and ht minus a here doesn't match. So what you need to do, you need to create another value so that it can be matched to t minus a and t minus a. So now, your ft minus a now should be t minus 4 plus 4. Why we have t minus 4 here? Because we want to make it similar term with h t minus 4. But even though we add another value in t here, we don't want to change t. So that's why we just plus with 4. Because if you expand this, t minus 4 plus 4, again we have t. We just create this minus 4 so that they have equal expression in terms of t minus a and t minus a. Okay, clear? Clear?
Better understanding.
Okay, so now,
Sort of get it.
okay, so now we want to have this transformation. When ft minus a is t minus 4 plus 4, then you know that ft equals to t plus 4. Just eliminate this. Okay, why? Because why we need to have ft? Because we want to have fs by transforming t plus 4 here. So you will have 1 over s squared plus 4 over s, transforming 1 by 1. So you have fs. Why you need to have fs? Because you want to transform. Here, you need to have fs. So, transforming t minus 4 plus 4 h t minus 4 is mapped to ft minus a h t minus a can be written as exponent negative as fs. So from here, exponent negative a is 4s, fs is 1 over s squared plus 4 over s. Clear now?
Yes, clear now.
Okay, so anyone has more question for this part? Any more question? Everyone's clear? Okay, let's try another example. Let's take a look at this example. Okay, in this example, as you can see, it is already written in terms of t minus a and t minus a. So, this is mapped to ft minus a, ht minus a. Right, because it is in terms of t minus a and t minus a. And you know that what is your a here? A equals to what? Okay, a equals to 4. And from here, you know that ft minus a equals to t minus 4 squared. Okay, so when ft minus a equals to t minus 4 squared, you know that your ft equals to t squared, right? Then you can have your fs by transforming ft, transforming t squared. So you have 2 factorial 2 over s cubed. So this is your fs. Okay, and since this expression is mapped to ft minus a and ht minus a, the transformation become exponent negative as fs, where exponent negative as and a is 4, so we have exponent negative 4s. Fs is 2 over s cubed. So this is how you transform. So for this case, no need to do like we did before, because we have already in terms of t minus a and t minus a. No need to make it similar. Okay, clear? Are we good? You can compare example 11 with the example that we did previously. This one, t only, ht minus 4. That's why we have to make it similar first. But this one, t minus 4 and t minus 4, it is already in terms of t minus a. So we just can use the property of second shifting there. Okay, clear? The symbol of what? Transformation? The transformation L here. Laplace transform ft equals to fs. All right. All of you clear or not? From 1 to 10, where are you? We have learned about unit step function, conversion between unit step function and step function, and how to transform unit step function, and then how to transform the second shifting property by using Laplace transform. The object t is equal to the object t minus a. What do you mean by the object t is equals to the object t minus a?
Doctor,
Yes.
I asked because for example 11, the object for the ft minus the object is t minus 4. Then after in the formula of the second shifting, it become ft. So is it these two t variable are same?
Okay, you mean why you need to change this from ft minus a to ft?
Because the t minus a and t, they are equal, right? And why the variable also no change, also two same t?
Okay. Why here I map to ft minus a? Because we want to make sure that it is in the form of ft minus a and ht minus a. Okay, so that you have to make sure in h, if it is t minus 4, then in f also it is t minus 4. Here and here. But this ft minus a is still a function of t. So when ft minus a is t minus 4, then ft, you just can omit that a value. That's why it becomes t squared. Both function ft minus a and ft here is still a function of t. The object is still t. Okay, but we have another constant of t minus a there. because we need to make sure this expression have equal expression. Is that clear? So from here, why you need to simplify from ft minus a to ft? Because we want to find fs. So that once you obtain your fs, you just can substitute here. Clear now?
Not very clear.
Okay, let's say,
Partially clear.
let's say you have fx equals to x cubed. Okay. Let's say you want to have fx plus a. Then it become x plus a cubed. Let's say fx minus a. Then it become x minus a cubed. But if you want to have fx back, again, you know that x only, x cubed. We just omit the constant there. Okay, so just like this, we map to ft minus a. So you know that ft minus a, originally it is ft minus a t minus 4 squared. So if you just want to omit the value of constant to get ft, still is a function of t, we just omit the value of minus 4. Then we have t squared. So from here, you can easily find the fs by transforming t squared directly based on the table of transformation. Okay, clear now?
Okay, more clear now.
Okay.
Thank you, doctor.
Okay, let's try another example. Okay, now, as you can see here, those ft minus a and ht minus a has an equal expression or not. Okay, this one we can map to ft minus a, ht minus a. Okay, but this is equal expression or not? Does these two expressions have equal t minus a or not? Yes, no, they are not equal. You cannot put that. Otherwise, if you put negative here, then this a is minus pi over 2 and this a is pi over 2, right? So it is not equal. So you have to make this equal first. Then what you need to do is to modify the term in cos here. To what? To cos 2. You have to create that minus pi over 2 without changing the original value. So this one, if you expand, it will become, this one is 2t plus pi, right? This one will become 2t minus pi. So you need to have 2t plus pi. So what you need to have here is plus with what? Plus with pi, right? Okay. Or plus with 2 pi. Right? If you expand this, 2t minus pi plus, sorry. This one plus with 2 pi. So you will have 2t plus pi. So same, right? Okay, clear now? Understand? This one. Okay. You modify this instead of t plus pi over 2. You want to have t minus pi over 2. So you just create that t minus pi over 2. But we don't want to change the original value. So we should plus with another thing so that we remain the expression. So we just plus with pi there. Okay, clear? Are we good for this part? Yes, in the function of cos. You don't want to change that. It is in the function of cos. Okay, so now what we need to do here, okay, clear not? So if you expand, then we can have what? This one. We can have cos 2t minus pi over 2, okay, plus 2 pi. So if you expand this, okay? So far so good up until here. Understand or not? Okay, so now this cos 2t plus pi over 2 h t minus pi over 2 now can be written to cos 2t minus pi over 2 plus 2 pi h t minus pi over 2. And you can see here, it is in the form of t minus a and t minus a. So we can map this ft minus a, ht minus a. Okay, so now you know, then ft minus a equals to cos 2t minus pi over 2 plus 2 pi. Right. What is ft? So what is ft here? Okay, so your ft is cos 2t plus 2 pi. Okay, now you want to transform. Here we can simplify the function first. Cos 2t plus 2 pi is equivalent to cos a plus b equals to cos a cos b minus sin a sin b. Then we can write here is cos 2t cos 2 pi minus sin 2t sin 2 pi, where this is 0, this is 1, equals to cos 2t, right? So when ft equals to cos 2t plus 2 pi, by identity, we can simplify it to cos 2t. So fs is transforming cos 2t will become s over s squared plus 2 squared, right? By table of transformation. Okay, understand or not? Clear now? So when it is mapped to ft minus a ht minus a, the transformation is exponent negative asfs. Then transforming this will become exponent negative as, where a is pi over 2 times with fs. So this is how you transform. All right, clear now. Okay. So basically, you always need to do some modification in order to make sure that t minus a of t and t minus a of h are equal. So this is how we do it. All right, let's try another example, which summarize the topics that we have learned so far. Okay. You have this piecewise function, express the unit step function, and determine its Laplace. Okay, try. Okay, what is your ft? What is a unit step function here? Anyone want to try? G1 plus G2 minus G1 HT minus A. So you will have okay, everyone got this? Then determine its Laplace. Okay, as you can see, this is only transforming constant, and this is mapped to second shifting property, but here t minus 2, here to t minus 7. Okay, try to make it similar expression first before you can proceed with conversion of Laplace there. Okay, anyone has problems with the first part here? I hope all of you can transform from step function or piecewise function to unit step function. Come on, guys. Anyone has problems with the first part here? All of you got this? Okay. Then transforming this. How to transform this? Anyone has problems on this part? Or you want me to explain again how to convert to make it similar term? Oh, you want me to explain? Okay. So now we have 4 here. So we have 2 expressions. So this is A, this is B, and everyone know how to transform A, right? So for A part, just transform constant will give you what? Transforming 4 will give you okay, thank you for our S. Now the B part transforming 2t minus 7 ht minus 2. Okay. When you have a function together with the unit step function, it is always mapped to transforming ft minus a, ht minus a, and by second shifting property, it is exponent minus as fs. But the first thing to do is to make sure that both f and h that has t minus a. And we cannot change this because t is minus 2 already. So we need to create t minus 2 inside here. So 2t minus 7. If you substitute this t with t minus 2, then we should add with what value to make sure that we can remain 2t minus 7. So 2t is 2t, 2 minus 2 is minus 4. So we have to put minus 3, so that if we expand this, we didn't change the original value of the function. So if you expand, you have 2t minus 4 minus 3, 2t minus 7. Same, right? Okay, so we can convert this to t minus 7 to 2t minus 2 minus 3, because we want to create this t minus 2 to make sure it is equal with ht minus 2. So now this transformation of 2t minus 7, ht minus 7 now can be written to transforming to t minus 2 minus 3 ht minus 2. Right? So as you can see, this is your ft minus a. This is your ht minus a. Then ft minus a equals to 2t minus 2 minus 3. ht minus a is ht minus 2 and a equals to 2. So when ft minus a is 2t minus 2 minus 3, then what is your ft? Okay, come on, what is your ft? Yes, 2t minus 3, thank you. Once you have your ft, only then you can find your fs by transforming this. Will give you 2 over 1 over s squared minus 3 over s. So this is your fs. This is your a. Then you can have your transformation. Will give you what? Will give you exponent negative 2s times with fs 2 over s squared minus 3 over s. So from here, you can have 4 over s plus exponent negative 2s 2 over s squared minus 3 over s. So this is how you transform one by one here. Is that clear? Any question? Okay, all clear? So this is how we transform. Okay, starting with understanding about your unit step function first. Okay, once you understand the unit step function, you can convert step function or piecewise function to unit step function. And then you can know how to transform a unit step function, ht minus a alone. And then we implement the second shifting property where that ht minus a is combined with another function. But you have to make sure that both function f and h has t minus a as their in their expression. Alright? So once they are similar, you just can use the property which equals to exponent minus as fs. Alright, from 1 to 10, where are you? Only 3 students from this class? What about the rest of you? All of you are busy with preparing for Hari Raya? Okay. Good value I can see. Even though it is 5, it is okay. Don't worry. Right? Okay. Can we proceed? Can we proceed, guys? Okay. All right. Another type of special function is Dirac delta function. Okay. We have done with unit step function. Now it is Dirac delta function. Okay. The transformation of Dirac delta function is quite easy. So you need to understand the definition of Dirac delta function first. Okay. This delta, okay, in a unit step function, ht minus a, it is equals to 0 from 0 to a, right? And 1 from a to infinity. But for this Dirac delta function, it is delta t minus a equals to infinity if t equals to a, and otherwise it is 0. Okay, so by definition, integrating delta t minus a from 0 to infinity will give you 1. And integrating from 0 to infinity for ft times delta t minus a equals to fa. So by using this definition, the transformation is like this. Transforming delta t alone equals to 1. Delta t minus a equals to exponent minus as. And then delta t minus a times with ft equals to exponent as minus fa. Okay, let's prove this first. Okay, now you want to transform delta t minus a. Of course, in proving, you always have to use the definition where you integrate from 0 to infinity exponent negative st times with delta t minus a with respect to t. Okay, and as you can see, integrating from the definition, integrating a function times delta t from 0 to infinity will give you fa. So now, what is your ft? Okay. What is your ft here? Ft here is exponent negative st. And if your ft equals to exponent negative st, then exponent FA will equals to exponent negative SA or exponent negative AS. So that's why integrate FT delta T minus A will give you FA. Then transforming delta T minus AS, delta T minus A will give you exponent minus AS because this is your FA. Okay, so now when you want to transform delta T only, then you know that A equals to 0. So transforming delta T minus A will give exponent minus AS. Then delta T alone will give you exponent to the power of 0, which equals to 1. Okay? Clear now? So now the next one. Transforming FT delta T minus A equals to exponent negative ASFA. So transformation will given by integrate from 0 to infinity exponent negative ST FT delta T minus A dt. So this one is your FT. Right, then your FA is equals to, when your FT equals to exponent negative ST FT, then FA equals to exponent negative ASFA. So this one, okay, this is how you prove. So whatever it is, in terms of proving process, you always need to come back again with the definition of Laplace transform. All right, so this is how we obtain the transform version of Dirac delta function. Is that clear or not, guys? Are we clear? Anyone has question? Or am I too fast? Please let me know. Which part? Which part that you want me to explain? All of it? All three? The third one. Okay. Okay, for the first and second, just refer to this. Okay, proving delta T minus A will give you this. Then proving delta T only. Then proving this delta T is referring to this delta T minus A only when you assume that A equals to 0. Then just put A here equals to 0. That's why we have exponent to the power of 0, which equals to 1. So now let's try to prove this. You want to transform Ft delta T minus A. Okay, and the transform is exponent negative AS FA. Okay, so by transforming this, by definition, of course, you have to have 0 to infinity exponent negative ST FT delta T minus A dt. Okay, and from the definition of Dirac delta function, from here, you know that integrating from 0 to infinity Ft delta T minus A will give you Fa. Okay, so let's say, okay, I try to make it more detailed. So let Gt equals to exponent negative ST Ft. So now we have integrate 0 to infinity Gt delta T minus A. Okay, so by definition, if Ft delta T minus A equals to Fa, then integrate 0 to infinity gt minus delta t minus a equals to ga, where ga equals to, here, just substitute a with t, exponent negative as fe. So, same with the product of transformation there. Okay, clear or not? Right? So this is how we prove where does the transformation comes from. Okay, now let's try to transform a function. Okay, don't worry, this Dirac delta function is quite easy usually because we only have ft there, not ft minus a. So now we want to transform this. So this is only delta. So transforming the function of ft here, we only transform exponent minus 2t plus transform direct delta t minus 2 here. Direct transformation, what will you get? Exponent minus 2t will give you what? Based on the table of transformation, exponent at will give you what? Now, exponent minus 2t will give you what? Okay, so 1 over s plus 2. And then this one, delta t minus 2. So delta t minus a. Delta t minus a, exponent negative as. So delta t minus 2 is exponent negative s. That's it. Okay, clear? Anyone has question? Right, out of 52 participants, all of you understand this? Where is Theo? Only Theo Chi Jin. Usually you are quite active. What happened to you today? Understand or not? Right. Understand, guys? Okay. Now let's try this example. We have t cubed delta t minus pi over 2. Okay. So this is you tak puasa. This is mapped to what? This is mapped to ft delta t minus a. Okay, in direct delta function, we have only these three. Delta t alone, delta t minus a, and the combination of ft and delta t minus a. Okay, so now this is mapped to ft delta t minus a. Will give you exponent negative as fa. So now how can we transform this? All right, you can see here. Ft equals to t cubed. And a equals to what? A equals to pi over 2. So when ft equals to t cubed, a equals to pi over 2, then fa equals to pi cubed over 8. So the transformation become exponent negative as times with pi cubed over 8. That's it. Okay. Okay, clear? For this part. This one, we just have ft. No need to change to ft minus a. So that ft minus a, ht minus a is only at second shifting property. Okay, clear? Are we good? Any question? All right. So let's take a look at the next one. Okay, example 16. By referring to example 15 here, try example 16. What should you get? Same process. You have your FT, you find your A, you have your FT and you have your A, you find your FA, and then that's it. Exponent negative A as FA. What should you get here? Okay. So now what we have done just now, we have done with transformation. Okay, and then there are properties, transformation. We have by definition, we have by table. Okay, and then we have learned about the properties. We have linearity. We have first shifting. We have multiplication by Tn. Now we also have what? Second shifting. Okay. Then we have special types of function. We have a unit step function. We have Dirac delta function, right? And now we have derivative delta function. Okay, after we have done with this all, only then we can proceed with inverse Laplace. So now you have learned all basic of transformation. Remember, our main focus is to transform. We have a function, we transform. Okay, we find the solution in S domain. Again, we inverse transform to get the solution in our original domain. So what we have learned just now is from Ft to Fs. There are many types of function that we have learned. Basically, we have constant, we have t to the power of n, we have sine, we have cos, we have cosh, we have sine. We also have piecewise function, right? And then we learn the properties. Now we know the special function where we don't have to transform the piecewise function one by one. We just need to convert the unit step function and apply or implement the transformation of unit step function. We have learned Dirac and now it is derivative. So all of these are the basic idea on how Ft transform to Fs. So what you have learned so far is from step 1 to step 2. Okay, and then after this we are going to learn how to inverse. Okay, once you can transform and once you can inverse transform, only then you can transform the derivative. Why? Because our focus is to solve differential equation. So in differential equation, of course, we have differential derivative. So this is how you transform the derivative. All right. There are derivation on how we obtain this one by one. So at least you can know how to transform. If you have y prime, it is sys minus y naught, where y naught here is the condition, IVP or BVP. After this, we can see one by one. But before this, we have to learn about inverse first. Okay, so this is just for you to know how to transform y prime to y, the y double prime to y triple prime to y. Once you can transform, only then you can solve the differential equation. Once you solve the differential equation, you obtain the solution and you apply the inverse transform to get our solution in the T domain. All right, are we clear enough? What we have been doing just now, are you on track? So you have to reflect yourself. Okay. Everything's clear? From 1 to 10, where are you? Up until this? Okay, you can try to do the exercise given there. Don't worry, once you understand, you can get the idea. Anyone has question so far? Wow, we are using the maximum duration for today's session. Okay, just now we have done with Dirac delta function, right? Okay, we have complete with this Dirac delta function. Okay, after this, we are going to learn about the inverse. How can we implement the inverse function? Once you know to transform and to inverse transform, only then we can solve the differential equation. So this is how to transform the derivative. So this is the form of solving the differential equation. Okay, basically we have learned this, right? But before this, we learned about how to solve it like directly from linear, from separation of variables, right? But now we want to implement the Laplace transform. Okay. So basically, we are still in this differential topic, but later we are going to solve it by using Laplace transform. That is the idea. Okay. Are we good? All of you? So before we stop, don't forget to scan the attendance. Wait, I'm going to give you the attendance. If you have no more questions, then that's it. So please do the exercise. If you have problem, you can ask me. Okay? Yeah. Why? Alright, so let's end our class with Suratul Az and Tasbih Farah for Muslim. Okay, so don't forget to scan the attendance here. So that's all for today. Happy holiday. Selamat Hari Raya. Take care and be safe, everyone. Assalamualaikum.
Thank you, Dr. Selamat. Selamat Raya, maaf Zahir
Semoga
batin, Doktor.
Doktor.
Welcome.
Raya.